difficult task, but very important task. We'll develop a method to solve quantum field theory, especially in particular Klein-Gordon theory, on whatever curved space-time, pretty much any one. So remember our strategy. We went from first quantization Hamiltonian formalism to the first quantization Lagrangian formalism because that was showing covariance. Then we allowed curvature, and we were still in the Lagrangian formalism. And now we are moving back to the Hamiltonian formalism. We are still at first quantization, and then we do the second quantization, and there we are. And then we are ready to do all sorts of things like cosmology and black holes. Here is what we did. We had we developed a formulation of Klein-Gordon theory, which was general relativistically covariant, accomplished by having this measure here and a metric. Using this action for the Klein-Gordon field and using the variational principle, we can derive the classical equation of motion, which is this. That's the Klein-Gordon equation when there is curvature in space and time. Well, it's also the Klein-Gordon equation when there's no curvature, and you just want to be able to do it in whatever coordinate system you choose, then this is the way to do it. And you see that the D'Alembert operator has become much more complicated. It's much more than just having second derivatives of space and time. Now, from the action here, we can read off the Lagrangian. We can read it off by simply dropping the time integration. And then we get the Lagrangian. The Lagrangian density we would obtain by dropping all of the integrations. But we are interested in the Lagrangian because we want to go from the Lagrangian then via a Legendre transform to the Hamiltonian, where we then, hopefully, can identify the degrees of freedom, phi and pi. Remember, one of the big problems we needed to solve was, what is pi? What is the canonically conjugate momentum field to phi? We expect that it's no longer just phi dot in the case of curvature. And it is indeed much more complicated than that. But we have a method. Identify the Lagrangian, then do the Legendre transform and get the Hamiltonian. And the Legendre transform will tell us what the canonically conjugate field is to phi dot, to phi. Okay, so here's the Lagrangian. Same as the action, but we drop the time integration. Now we do step 3. Remember, that was this one. Lagrangian to Hamiltonian. And here's how we do that. The Lagrangian depends on the phi and its space and time derivatives, where the time derivative is really what we ought to call the beta field, right? Now, and the beta field is the canonically conjugate to the pi of the Hamiltonian. Now let's do this. We do the Legendre transform from the Lagrangian. It depends on those fields, phi and phi dot, which was the beta field, to the Legendre transform back to h, which will depend on phi and the mysterious pi. Well, it's not really mysterious now, because we know that the Legendre transform is obtained by introducing a new variable, which is the function L that we want to Legendre transform, functionally differentiated with respect to the variable that we want to Legendre transform, which is the phi dot. Phi dot or phi comma 0 is the same thing, of course. And that is going to be our pi. Then what we have to do is express the Hamiltonian as, the sum over new variable times old variable minus the old function, as the Legendre transform always works. But we are now ready to read off what the pi is. And it'll be rather complicated. We could not have guessed that. So the functional derivative of the Lagrangian with respect to phi dot is what? You have to functionally differentiate that expression with respect to phi dot. Now where does phi dot occur? Phi dot is phi comma 0. It occurs here and there, in the same way that we'll just get rid of the factor 1/2. So whatever comes up twice. There's no phi dot here. You'll have a contribution from here. And what is it going to be? Well, it's going to be, for example, if we differentiate this term with respect to the phi comma 0, then we are left with dropping that term, dropping the integral, and what's left over is a measure factor, is this term summed over that, where the nu has to be 0. So that here we have the phi dot. Okay, and we get twice that. So, here it is explicitly. The pi field is dl by d phi dot, and that is the measure factor over here. And then we have whatever's left over, namely this times that twice, because the symmetry here, we get rid of the 1/2, so it's this times that, but the nu has to be 0. That's what it is. There's a g mu 0 sum over phi comma mu. Which means that it's really more complicated than just phi dot. Pi is containing phi dot, because this sum over all mu has also the case where mu is equal to 0, and that's just the phi dot. But even that gets multiplied with the measure factor and with the g naught naught. But then there are also other terms. In particular, there are terms of the spatial derivatives of phi. They also occur in pi. Remember that this is not just because of curvature, this is also because we allow arbitrary coordinate systems. Okay, now remember that when we do the Legendre transform, then we define a new variable in terms of the old variable phi dot, but we must be able to invert that relationship. Not a problem here. We can solve that equation for phi dot, so that we can then express phi dot in terms of pi, and whatever else might be around, such as the spatial derivatives of phi. So explicitly, if we write out that sum here, this sum over mu from 0 to 3, then we obtain that this equation, when spelled out, is that pi is the measure factor times g naught naught phi dot, that's the first term here, plus, and then the sum over the space coordinates, g naught I phi comma I. Of course, in Minkowski space in Cartesian coordinates, the measure factor is 1, and the g naught I is 0 because the metric in Cartesian coordinates in Minkowski space for an inertial observer is diagonal. So then we recover the usual relationship that pi is phi dot. But in general coordinates, and especially if there's curvature, this is what the canonically conjugate momentum field is. And that equation we can solve for phi dot. Namely, if we put phi dot on one side, we obtain that phi dot is pi over g naught naught minus these expressions here. This is what we need, because the Legendre transform requires, the Legendre transform that gets us from the Lagrangian to the Hamiltonian requires that the Hamiltonian is given by the integral over the new variable times the old variable minus the old function. This is the Lagrangian here, where all occurrences of the old variable phi dot have to be replaced by phi dot expressed in terms of the new variables. So we have to express phi dot in terms of pi and other things. And here too, in the Lagrangian, we have to express all occurrences of phi dot in terms of pi and other things. So we have to simply use this expression. Every occurrence of phi comma 0 is replaced by this, which is pi, and spatial derivatives of phi. These are all parts of the new variables. So you see, it gets a little tedious, but straightforward. You just take this Legendre transform expression and replace all occurrences of phi comma 0 by the right-hand side of this equation. And I leave it to you as an exercise to put that in there and then simplify as far as possible and then compare the Hamiltonian that you get with the Lagrangian. Now we do know from the general framework of Legendre transform what happens to the equations of motion. We don't have to do it in every single case. We solved it in generality. We showed that after you do all of this and you calculate the Hamiltonian, then you obtain the equations of motion, and they come out to be this. They have to, because it's always what the Legendre transform does. So the d by dt of phi, the time evolution of phi, is going to be the functional derivative of h with respect to pi, and the time derivative of pi is given by dh by d phi, the usual Hamilton-Jacobi equations of classical mechanics. And again, it would be a good exercise for you, if you like, to verify that these equations, and spell out what these equations are for the actual Hamiltonian, and verify that they imply the Klein-Gordon equation. So covariance is not broken. Yes, we did single out time now because that's in the nature of the Hamiltonian formalism, but we didn't break covariance because we only reformulated things. We made sure everything is generally relativistically covariant by doing it with the action, and then we simply transformed things. We didn't change them, we just transformed them using the Legendre transform into another way of writing things, and by doing so we did not break the covariance. But yeah, in the Hamiltonian formulation, time is singled out, and that's in the nature of things because the Hamiltonian is then used as the generator of time translations. In fact, this is what those equations mean. The Hamiltonian is the generator of time translations. That's exactly what it means to have equations like this. So we are now ready to second quantize. We arrived here. We have classical fields here. The phi and the pi did not carry hats. They were still classical fields. But it was the Hamiltonian formalism, and we have curvature, or we allow curvature. We can now do the step to second quantization, the quantum field theory on curved space-time. This amounts to the following. The second quantization amounts to solving three problems. The first is to find operator-valued fields phi hat and pi which obey the canonical commutation relations. And the second job is to make sure that these operator-valued fields as functions of space and time are Hermitian, that they're formally self-adjoint as operators. For every x and t, this should be a self-adjoint operator, and the same for the canonically conjugate momentum fields. And remember that the pi field is not phi dot here, it's this complicated thing. And the third job is, well, that we make sure that the fields phi hat and pi hat of x and t obey the equations of motion. Right? So equations of motion, hermiticity, and canonical commutation relations. These are the three things that we need to solve. And the equations of motion in second quantization are expressed like this. The time evolution of any observable is given by 1 over I h bar, that observable commuted with h. And you can apply that to an observable such as phi or pi and so on. Explicitly, we know that the equation of motion that we have to fulfill is this one, the Klein-Gordon equation. After all, when you quantize, the equation of motion in the Heisenberg picture does not change. And ultimately, that's because the Poisson structure of the classical and the quantum theory are the same. If you'd like to know more about that, send me an email. I can send you lecture notes on that. So we do know, on completely general grounds, but we could also work it out explicitly by calculating the Hamiltonian, calculating those commutators, but we know beforehand that the Klein-Gordon equation is what is still to fulfill here. This equation for phi implies the Klein-Gordon equation. And when you write it down for pi, you get this relationship. You know, what we just derived earlier, the expression of pi, the canonically conjugate momentum field, in terms of phi dot and space derivatives of phi. All right, so we have our work cut out for ourselves. We need to solve those three things: canonical commutation relations, hermiticity condition, and the equations of motion. What we'll do today is prove. We will prove that there is a method for doing this, for solving those three things, no matter what the space-time is. I mean, yes, there are some conditions on the space-time, but we will not need any symmetries, any particular niceties of the space-time. So it could be, you know, a really messily evolving space-time. Now, to get to that method, to prove that this method always works, at least in principle, it may be very hard to carry out in practice, but we will show how to do it in principle. And then when there are some nice symmetries, then you can actually do it in practice too. And even when there are no symmetries, this gives you a method for working it out, if need be, numerically with a computer. So in order to get to that method, let us remember how we solved the Klein-Gordon theory on Minkowski space, and then try to figure out a way to generalize that for generic curved space-times. So the solution in Minkowski space looked like this. I'm just rewriting what we developed much earlier. So the field as a function of space and time is given by this normalization factor, and then 1 over square root of 2 omega k. And then we had these functions here, so-called plane waves. And then we had the creation and annihilation operators. And if you look at this, at the structure of this solution, then you can see that it suggests a strategy for generally solving quantum field theory, also on curved space. Namely, look at the structure. This part is real, and that part is the Hermitian conjugate of that part. This tells us that the hermiticity condition is going to be fulfilled, right? Phi dagger is phi. That's clear because this is the dagger of that, and this piece is real. So that suggests that in order to solve the quantum field theory, the Klein-Gordon theory, on a generic curved space-time, we may want to do a similar thing. Write down something here, and then add to it the Hermitian conjugate of it. That will make sure that the hermiticity condition is out of the way. It's guaranteed. Secondly, let us look at the equation of motion, the Klein-Gordon equation. How can we see that this is obeying the Klein-Gordon equation? Well, the Klein-Gordon equation is a differential equation in space and time. Never mind that stuff. It doesn't depend in space on time. And this integral here is an integral over k. Again, no space sorry, no space or time dependence there. As far as solving the Klein-Gordon equation, the only thing that matters is the space and time dependence, and that's only in here, well, and in there. So in order to make sure that we have a solution to the Klein-Gordon equation, this function here, that has to be a solution of the Klein-Gordon equation. And indeed, for every k and omega k, this is a solution of the Klein-Gordon equation. Easy to see. In Minkowski space, for the inertial observer with Cartesian coordinates, the D'Alembert operator is just, you know, dt squared minus dx squared. And that is a solution here, given that omega k is given by square root of k squared plus m squared. So the point is that by putting here a function that solves the Klein-Gordon equation, and then of course here the complex conjugate of it, if we put here a solution to the Klein-Gordon equation, and by that I mean a classical solution of the Klein-Gordon equation. It's not operator value, it's just a number-valued solution of the Klein-Gordon equation. We are already guaranteeing that this thing is going to solve the Klein-Gordon equation as an operator, right? Because there are operators here too. And that's because the only space and time dependence is here. So that suggests that when we later make an ansatz for solving the Klein-Gordon equation on any curved space-time, we may want to have this structure of something here, here's the complex conjugate to get the hermiticity condition, and have a function here which solves the Klein-Gordon equation. There may be many different solutions, but any one of them we can use. In fact, we will have to add a lot of them, perhaps. As you see here in Minkowski space, one solution alone will not do. We have an integral of lots of them, integral over k, right? And for every k, we get another solution of the classical Klein-Gordon equation. Well, and then the third condition after hermiticity and equations of motion was to get the canonical commutation relations right. And here, from the Minkowski space solution, we read off that we do it by having here A and A dagger operators and require them to have the usual commutation relations between A and A dagger operators. Commutator is equal to the Dirac delta. That's definitely, if we put such operators in here, this will definitely make this operator valued by making sure that they do not depend on space and time. We are not interfering with solving the previous problems, hermiticity and equations of motion. So we are certainly free to add here operators like this. Of course, they have to be Hermitian conjugates of another, not to screw up the hermiticity condition. But we are certainly free to put any kind of operator here and sum this up. The thing is, we must make sure, and that's the difficult part, we must make sure that the commutation relations between A and A dagger actually imply the proper commutation relations between phi and pi. That is the reason why we have to have these specific prefactors here. These specific prefactors and the fact that we need an integral over all of R, that's only to ensure that the commutation relations between phi and pi that we want are actually implied by the commutation relations between the A and A dagger. That will be the difficult part. So let's replicate that strategy. Here it is. The strategy is we will ensure hermiticity and we will ensure the equations of motion and the canonical commutation relations with this ansatz. So the ansatz is that phi is given by a sum over k. This could also be an integral. I'm just writing here a sum. It doesn't really matter. It could be sum or integral, depending on whether or not you have a box regularization or what choice of basis you want to use. It's just that then you don't need to worry with Dirac deltas. You get Kronecker deltas, which might make things a little easier. So we write our field. We try to find a solution similar to this, where we write it as a sum over some functions that we will want to be solutions, classical, number-valued solutions to the Klein-Gordon equation times an annihilation operator plus the Hermitian conjugate of that. And then we know already what we need for pi. Pi has to be this expression. It's no longer phi dot, it has to be this expression. Now that's well motivated, I guess, because this ansatz will guarantee hermiticity. It will guarantee the fulfillment of the equations of motion, right? Because this is not dependent on space and time. That's not dependent on space and time. And these are required to be solutions to the Klein-Gordon equation. And the Hermitian conjugate is also a solution to the Klein-Gordon equation. The Klein-Gordon equation has no complex coefficients. It only has really valued coefficients. So any solution to the Klein-Gordon equation will have the property that its complex conjugate is also a solution, right? So if U is a solution to the Klein-Gordon equation, U star is as well. Okay, so with this ansatz, we have right away the equations of motion fulfilled, and right away the hermiticity condition. The difficult part is to ensure that we can have the canonical commutation relations, that phi pi commutator equal I h bar Dirac delta is guaranteed by the commutator of A and A dagger being the Dirac delta. That's the non-trivial business. What we'll show today is that this is always possible. This ansatz always goes through. Of course, at that point, we still then have, after we've proven it, we still have to find those solutions. But remember that that is boiling down to a classical problem. Finding UKs is the problem of finding number-valued solution to the Klein-Gordon equation. So we're reducing the quantum field theory to a classical field theory. And with sufficient symmetry, you might be able to give those UK explicitly. Oh, and then we'll have to address the question of, after we prove that such UKs exist, we'll have to address the question, are they unique? And they're not going to be unique, and there's a huge physical implication. There's an important physical meaning to the fact that the UKs are not, there's not a unique choice. There are many solutions, in fact. Okay, so we will use these commutation relations between the A and a dagger. That will be very convenient. Oh yes, what I want to say is that these UK of x and t, these guys here, that are central to the entire ansatz, they will be called the mode functions. Okay, so we try out this ansatz. The Hermitistic condition, as we already discussed, holds by construction. The first equation of motion, the Klein-Gordon equation, holds by assumption, right? Because we are saying that the field is a linear combination of solutions to the Klein-Gordon equation, and the rest, the A and A daggers, don't depend on space and time. So therefore, it's guaranteed that if we find those, if we choose UK functions that are solutions, that are number-valued solutions to the Klein-Gordon equation, then yes, this operator-valued field is going to solve the Klein-Gordon equation as well. Notice, though, a curiosity here. The classical field theory of the Klein-Gordon field is a theory where the Klein-Gordon field is real number valued. But for the quantum field theory, the classical solution that we need is going to be a complex valued one. Right? So it's not like we really reduce it to the classical theory. We reduce it to finding the solution, a complex valued solution to the Klein-Gordon equation. Otherwise, this would be the same as that. And as we will see later on, that would not be consistent. Can't have the commutation relations with a real valued u of k. They have to be complex valued. Anyway, that's just as an aside. Okay, so we have the Hermitistic condition fulfilled automatically. And also, since we are assuming that we choose UKs here which solve the equation of motion, the phi hat is going to solve the equations of motion as well. The second equation of motion, which is the relationship between pi and phi, is going to be obeyed as well simply by construction. We define pi to be the expression that solves that, right? If you remember, our ansatz was that phi can be expressed in terms of these to be determined functions, and the pi is given by this by definition, and that is the second equation of motion. So really all we have to show here is, at this point, is that there exist such functions UK such that this ansatz will succeed. Right. Okay, so now the task is to check the canonical commutation relations. This is the key canonical commutation relations. The other ones, think about it, why they are fulfilled. The phi pi canonical commutation relation is the key one. It's simply this. And in order to verify that we can fulfill these canonical commutation relations, all we have to do is plug in our ansatz. So our ansatz for phi was that it can be written in this form. We'll plug that into here. And we also had in our ansatz that the pi field is given by this, the second equation of motion. So we'll plug that into here. And you can see how this is getting complicated, especially because pi is not only this. In here, the phi needs to be expressed in terms of our ansatz again, right? So you see what's going on? We have to put the phi in here, and we have to put the pi expressed in terms of the phi also in there, and then check and verify the canonical commutation relations. So pi is given by this because of the second equation of motion, but the phi has a particular form according to our ansatz, and so the pi is really given by this long expression here. There's nothing really went on here. This is just exactly the measure factor, the metric, and the derivative measure factor, metric, and derivative acting on phi expressed in terms of our ansatz. This one. Okay, so now we plug this and that into the canonical commutation relations up here in the top, and we obtain this messy thing here. Okay, so the commutator between phi and pi at equal time but different points in space is given by this. Here you recognize our ansatz for phi, and here this is our ansatz for pi that we just calculated. We're going to get some contributions, but not as many terms as it looks like. We only get contributions when A commutes with a dagger, so these two will give us a term, and also the A dagger with the A. The A commute with the A, and the A dagger commute with the A dagger. So what we get is two terms. When we commute the A with the A dagger, then we get a term where we have this in front and that. That gives us here the U, and then here we get this derivative term, and then there's this overall prefactor as well. I pulled it in front over here. And then there's the term where we have an A dagger and an A. Here the commutator gives us a minus sign, because the commutator between A dagger and A gives us a minus Dirac delta. So all of this has deltas, multiplying deltas, because the A and the A. See, remember that here we have a sum over all k, there we have a sum over all k prime, and so we only get non-commutativity when k is equal to k prime. That's why we get the deltas here. It's a Kronecker delta because I assumed the k variables to be discrete, but if you choose them continuous, then you would have a Dirac delta. Oh, this may be a good point to remind you that this k has no reason to be the momentum. In Minkowski space, it might be a good idea to try that, because we know that then we get the standard solution. But in curved space-time, there's absolutely no reason for, in this ansatz here, where is it? Here's our ansatz. There's no reason for the k to be the momentum. In fact, what the hell is the momentum in curved space-time? You can't just Fourier transform. I mean, yes, you can, but if you chose a different coordinate system, you'd arrive somewhere else. Fourier transform is not covariant. So there is no canonical choice for those k's. I mean, yes, if there are symmetries, scaling vector fields, and so on, then there may be a canonical choice, but generically there isn't. So the k is just some variable which in Minkowski space conveniently can be chosen to be the momentum. But in generic curved spacetimes, no, this is just a sum over number-valued solutions times operators that act like creation annihilation operators. This is pretty abstract here. It works even when there is no notion of momentum, or no canonical notion of it. Okay, so we are checking the canonical commutation relations. We arrived here. So now let's consolidate the this expression here by carrying out these double summations with the Kronecker delta, leaving us with only one summation, namely when k prime is equal to k. So now we are left with this expression here. Same as above, just the Kronecker delta is carried out to get rid of one of the summations. And here we are. And this complicated expression is supposed to equal I times the Dirac delta, because we want this commutation relation. And if our ansatz is to succeed, this is the key message here, if our ansatz is to succeed, then we must be able to find a bunch of functions UK such that this expression in terms of those functions equals the Dirac delta. That's a rather non-trivial task. We are asked to find a set of solutions to the Klein-Gordon equation, a set of solutions UK, such that if you plug them into this expression, differentiating them, taking the complex conjugate, and doing the complex conjugate of that, taking the difference between the two, sum over all of those, and multiply with this measure factor here, then that should just be I times the Dirac delta. How do you go about finding such solutions that will do this? In fact, at the moment, we are concerned with the question whether there is actually such a set of solutions. Why should there be? Why should there be a set of solutions to the Klein-Gordon equation which obey this weird condition here? And notice too, it's not easy for functions that are solutions to a differential equation to sum up to a Dirac delta. This is a distribution. Each one of those terms in the sum here, each one of them is just a regular smooth function, right? The Klein-Gordon equation is a very well-behaved differential equation. It has smooth coefficients. Its solution should be smooth. So each one of those UK functions, each one of those solutions to the Klein-Gordon equation will be smooth. And when you differentiate them, still smooth. When you multiply them, still smooth. And then you take the difference, still smooth. But we need the Dirac delta over here. So we need to sum up infinitely many of them to have a chance to produce a distribution out of smooth functions. That's why we need an infinite sum here. Otherwise, if that weren't the constraint, the commutation relations weren't the constraint, if that weren't to be fulfilled, we could just choose one of those functions, perhaps. The hermiticity condition and the equations of motion are always fulfilled, even if we just take a partial sum of all those k's, or just one k. No, it's the commutation relations that require us to solve that particular equation. And notice, it's really a matter of differential equations here, a matter of ordinary functions, right? Nothing to do with operators at this stage. We just boiled it down to finding solutions to the Klein-Gordon equation. It's just finding a particular class of functions. Yep?
Is it strict that we need to choose A and then gather to formulate in that way?
No. Some authors will make an ansatz in which some dependence on X, for example, is incorporated in the A's and in the A daggers. You can do that basically by doing an analog of a Fourier transform. But this makes sense in special circumstances, when you have particular symmetries, when, for example, you have a notion of Fourier transform, then it makes sense. But when you do it very generally, then I think this is the way to do it. You could, of course, always by hand, just instead of using the A and A dagger that have on the right-hand side of their commutator a Dirac delta or Kronecker delta, you could choose some that have 7 times the Dirac delta or something like this. That would simply imply that you have to renormalize your UNs and UN stars. If you want to change the commutation relations in a more severe way, such as that the commutator between A and A dagger is, I don't know, A dagger squared or something like that, then you're back to square one. Because then you have to show that you can actually make the phi and phi dagger, the phi and pi commutation relations come out right with this representation, right? It would be a different ansatz, and it may or may not succeed. What we did here is we made an ansatz. We made an educated guess for what might work. That's what an ansatz means. And so this is an educated guess for what might work, and now we're proving that it does work. And other things may work as well, but you have to show it. So that's a non-trivial thing to do then.
But my concern is, will it give a different I mean, because the answer, the constraint of the commutations between the fields, you can view it as we are viewing it now. We need to find like that specific.
We will address that very question in the next lecture. We will be able to make use of the Stone-von-Neumann theorem, which says that the same commutation relations may have different representations, but they still describe the same physics, as long as you have finitely many of them. So if you properly regulate your quantum field theory, then it doesn't ultimately matter which representation you choose. So then it's just a matter of convenience. There may be other ansatses that you can use, but they would be unitarily equivalent. But that same question comes up again later, also next lecture, when we will study what if there is not just one set of the UNs, but maybe there's another set of UNs as well that will do the trick. And then, which is the preferred choice? Stone-von-Neumann's theorem will say, well, your choice. It doesn't really matter. It's the same thing, just a change of basis in the Hilbert space. But it will make a difference when you assign meaning to the states in the Hilbert space, because each choice of UNs comes with a choice of A and A daggers, and they come with a state that's annihilated. And of course, we would prefer to choose that set of UNs whose associated A operator annihilates the vector which we, for other reasons, know is a vacuum state. That would be a convenient choice. But we are always free to choose whatever solutions we want here, as long as they obey the conditions. And we get different A and A daggers, we get different Hilbert space, Fock space constructions. They all describe exactly the same physics. It's just that some of those constructions are more convenient than others for identifying which state in the Hilbert space is actually the vacuum state. That's important because once we know what the vacuum state is, we can then deduce what the 5-particle state is and so on. All right, so our conclusion so far is that this ansatz, where A and A dagger obey the standard raising-lowering operator commutation relations, where the UN are solutions to the Klein-Gordon equation, solves the quantum field theory, that is to say, solves the hermiticity condition, the equations of motion, and the canonical commutation relations, if we can find a set of solutions to the Klein-Gordon equation, UN of x and t, which obey this weird condition here. Rather messy-looking thing. But how do we know that there are such solutions? Shouldn't we just throw up our hands and say, well, it would be nice if we had a set of solutions that obeys that condition, but how on earth do we know that there is such a solution, such a set of functions? So our task now is to prove that this ansatz actually always succeeds. At least in principle. I mean, you may not be able to find those UK explicitly, unless maybe numerically, but let's prove that they exist. Okay, so how do we know that the ansatz always succeeds? That we can write the quantum field of the free Klein-Gordon field in curved space-time always in this way? Okay, we have to make an assumption about space-time. We will assume that it's globally hyperbolic. Those of you who took my course last term will remember that. What it means is that the space-time possesses a foliation into Cauchy surfaces. That there's a well-defined slicing of space-time into equal time three-dimensional hypersurfaces. That is topologically it's of the form of R cross M, where M is some manifold. So on such space-times, you do not have closed time-like curves. And in particular, we have a well-defined initial value problem. So if you know what the field conditions are on any one of those Cauchy surfaces, then you can calculate the future. Now, the proposition is that for such space-times, indeed, such a set of functions UK will exist. A set of solutions will exist that sums up in this term up there to the Dirac delta. and therefore our ansatz will succeed. In fact, we will have an abundance of those solutions, and we will have the freedom to pick any one of those sets of solutions to build up our Fock space and so on. It's always the same physics, but generally every observer will have his or her best choice in the sense that it's most convenient because the vector that's annihilated by the A operator will be the vacuum. But different observers may not agree on what that is. But they still describe exactly the same field, the same physics. It's just a question of what they call the vacuum. So the ambiguity in choosing which set of solutions you choose translates into the ambiguity of what is the vacuum, as we will see later. It's not supposed to be clear just yet. Okay, so now we have to prove this. In the literature, they tend to glance over this very quickly. But again, since it's such a crucial thing, let's do it carefully. So we will need to study the space of solutions to the Klein-Gordon equation. Because the question is, in that space of solutions of the Klein-Gordon equation, can we pick out a bunch of those solutions, UK, which obey this condition W, the condition that when you differentiate, multiply, take differences, and so on, it all sums up to the Dirac delta. So we'll have to study the structure of the solution space of the Klein-Gordon equation on generic curved space-times. So let's consider a vector space V, or that vector space V, of all, initially, just the real valued solutions of the Klein-Gordon equation. Now, it turns out that the space of real valued solutions of the Klein-Gordon equation has an inner product. Or more precisely, it's not quite an inner product because it's not, well, it's a bilinear form. So we have a vector space, the vector space of solutions of the Klein-Gordon equation, and we define this bilinear form according to this definition. So assume that F and H are solutions of the Klein-Gordon equation. Number valued, in fact, real number valued solutions of the Klein-Gordon equation. Then we associate to the pair a number. So the bilinear form associates to the two solutions F and H this number here. You calculate it by picking out a surface of equal time. So you choose in your space-time a coordinate system, and then you pick one time, and at that time you integrate over all of space. You're integrating over a space-like hypersurface. That's the integration measure over that space-like hypersurface. And this is your integrand here. You see it's H times the derivative of F, and here F times the derivative of H. And then you contract the indices, here's a measure factor, and so on. This is a bilinear form because if you plug in 5 times F, then the 5 occurs here and there, and you can pull it out. It's linear in F. It's also linear in H. So it's a bilinear form. But it's also anti-symmetric. If you interchange F and H here, then you get minus this, because then simply those two terms get swapped. So it's an anti-symmetric bilinear form, which is a symplectic form. You may wonder, doesn't it depend on what surface we choose here? We integrate over one time, right? Could it not be that if we integrate this over a later time, we get a different number? We will have to show later that we don't. It doesn't actually matter at what time we do this integration. Clearly, that's not trivial. To prove it, we will need to use the equations of motion, which we can because F and G are not arbitrary functions. They are solutions to the Klein-Gordon equation. And we will use Stokes' theorem. But for now, let's just take this definition here. And we will just take the statement at face value that this bilinear form is independent of the choice of space-like hypersurface on which you integrate it, on which you evaluate it. Okay, so FH is a symplectic form. It's anti-symmetric. Now, what can we do with such a thing? This is not like a regular Hilbert space inner product, right, which would be symmetric. However, there's a theorem which goes back to Darboux, and what it says is that whenever we have a symplectic form, or non-degenerate symplectic forms, I mean, it would be degenerate if there was a big blob of zeros, or a smaller big blob of just zeros, which we don't have in this case. So the theorem says that for any symplectic form, there exists a basis in the vector space, in our case, the vector space of solutions of the Klein-Gordon equation, such that in this basis, our symplectic form takes this particular shape. It consists of those blocks here of 0, 1, minus 1, 0, 0, 1, minus 1, 0, and so on. You can also reorder them such that you have 1s here and minus 1s there. Okay, so what we get is a bunch of, there's a basis. What this theorem, what Darboux's theorem says is that when we have a vector space with a symplectic form on it, then there exists a basis, in our case a basis of functions that solve the Klein-Gordon equation, a basis Vn such that in that basis, this is how the symplectic form looks like. Concretely, the Vn, the V2n solution, symplectic form with V2n plus 1 is 1, and 2n plus 1 with 2n is minus 1. And all the other components vanish. So what that means is that if we take an arbitrary vector in the vector space, or solution of the Klein-Gordon equation, then we can expand it. So in particular, if, let's say, A and B are vectors in the vector space, in the symplectic vector space, then we can write A as a linear combination of those solutions, and B as a linear combination of those solutions. And then the bilinear form applied to the solutions A and B gives us this sum here. Now with the plus signs here and the minus signs from there. Okay, so this is a bit like diagonalizing a self-adjoint operator, but it's not. This is, in this case, a symplectic form. And unlike in the case of a self-adjoint operator, which has a unique diagonalization, the Darboux theorem says that a symplectic form doesn't have a unique diagonalization. There are others as well. Mm-hmm.
Do we have anything to guarantee that the symplectic form in this space is not degenerate?
We would have to go into the differential equation and check its properties. That's right. You have to trust me on that. Right. Yeah, in principle, what that would mean is that, it could be that there are solutions to the Klein-Gordon equation that are non-zero, and yet their inner product, not the inner product, bilinear form of them would be zero even with themselves. Right? So that will not happen. Okay, so now assume we picked one of those bases. Yeah, keep in mind, those bases are not unique. Okay, but let's say we pick one. We pick a basis Vn, and then remember that V is the space of all real-valued solutions of the Klein-Gordon equation. We proved our things now for real-valued solutions of the Klein-Gordon equation. Let us look at the complex-valued solutions of the Klein-Gordon equation now, because given the i's that were floating around earlier, we should expect that we need them. So let's see how what we found for the real-valued solutions translates into properties of the larger vector space of complex-valued solutions of the Klein-Gordon equation. Let us call that vector space V bar. Now we can easily find a basis for V bar. Namely, we can define functions un, which are linear combinations of a solution of a real-valued solution plus I times another real-valued solution, neighboring ones according to the Darboux diagonalization. So we take the V2n and the V2n plus 1. Remember that in this matrix here, you always have this 2 by 2 blocks here, right? We take those two and combine the two vectors of one of those 2 by 2 blocks, combine them into one complex solution. Right? There are really two real-valued solutions, but we can combine them into one complex solution. That's what we do here. We take that solution plus I times the other one of that 2x2 block, and then we get another linearly independent solution by taking the complex conjugate of it, and that will just change around the sign here. So we have two independent complex-valued solutions now. Since the Klein-Gordon equation has real-valued coefficients, this will get us all of the solutions, because all of the solutions are spanned by the real-valued one. Right? Because if you just by linear combination, if you take a real-valued one plus I times a real-valued one, that's a complex-valued solution, and all of the complex-valued solutions arise this way. So now we have another basis. Now we have a basis of the space of complex-valued solutions of the Klein-Gordon equation, and the basis is given by the basis functions un and the basis functions un star. What is the natural product now on this space of complex-valued solutions? Well, here is a natural product. We define the bilinear form between f and h to be given by this expression here. And it turns out that this has very nice properties. And by the way, this is covariant. In other words, it's independent of the choice of space-like hypersurface on which you do the integral for the same reason as the previous was, because it's really just the same thing, just rewritten a little bit. So from the double diagonalization that we had for the real-valued solutions, we obtain, without further invoking any other theorems, we obtain directly from the properties of the round bracket, we obtain these properties for that square bracket. This is, of course, nothing to do with the Dirac brass and Ketz, right? It's just another inner product on that vector space. So what we obtain is that the inner product, this covariant inner product between two solutions, two complex-valued solutions, gives us a minus Kronecker delta if you take two of the u's, and you get a plus Kronecker delta if you take two of the u stars, and they are orthogonal with regard to that inner product here. The u's and the u stars are orthogonal with respect to that inner product. You have to be careful, though, because it's not properly an inner product. It's an indefinite inner product. Because, so to speak, the length of vectors doesn't always come out positive. Here it comes out positive, but those have technically negative length squared. So it's not a proper, inner product or inner product space. It's an indefinite inner product space. So it's not a Hilbert space per se. However, oh, and by the way, as an exercise, plug this in and show that from the double diagonalization you get these expressions here. It's not a Hilbert space, but as I will mention in a moment, you can make one out of it. So this bracket here is an indefinite inner product on the space of complex-valued solutions of the Klein-Gordon equation. And if we write it out as a matrix, that's what it is. Minus ones and then plus ones. This means that we can write down a resolution of the identity on the space of complex-valued solutions of our Klein-Gordon equation. Namely, the resolution of the identity can be written as identity equal to sum over all n, and then here we have these un's with a minus sign, and these guys with a plus sign. It's just the resolution of the identity. Why? You see, let's check. If we apply the identity, this proposed identity, on the un, we get the un back. And that's because if you apply this to a un, I mean, here this will go away because they are orthogonal, as we just established. But if you apply a un here, you get a minus 1, you get the un back, and there's another minus, so you get the plus. If you apply this proposed identity on the un star, then this will not contribute because they're orthogonal. And if you apply it to a un star, well, it will pick out and it will be 1, it will be Kronecker delta, it will pick out the right term here and you get the identity. So it's a resolution of the identity in the space of complex valued solutions of the Klein-Gordon equation. This, by the way, also means that we can turn the space of complex valued solutions also into a Hilbert space, the so-called Krein space associated to that symplectic form. But we won't need to do that. I give you a bit more details here written in the small print in black, if you are interested in that. The point is that we get a resolution of the identity. And the resolution of the identity is this. Okay? Where, if you remember, this bracket here is defined in terms of the round bracket, and the round bracket is defined in terms of, this bracket is defined like that, which is just a rewriting of this round bracket over here. Where is it? Oh, so far. Here we go. There it is. Okay. All right. So what we showed is that by using Dabou's theorem is that there is a basis which puts that symplectic form into a particular shape and which then provides a basis, the UN, which gives us a resolution of the identity in the space of complex valued solutions of the Klein-Gordon equation. Here is this resolution of the identity when applied to a function f, for example. Applied to a solution f. It's not just arbitrary functions. We're dealing with solutions of the Klein-Gordon equation. Now, the claim is that this resolution of the identity, when we actually spell it out as functions, not just as abstract vectors in the space of solutions, but when you write it out as actual functions, is the condition that we have to fulfill. It happens to be exactly the condition that is needed to ensure that our ansatz succeeds and the phi-pi commutation relation is reduced to the A-dagger commutation relation. Okay, so the statement is that this is this. Okay, how do we see that? Okay, so this bracket was defined in this way. And now let us choose a coordinate system so that we can make this stuff explicit. So we choose a coordinate system on our space-time, and we pick a time, and then the integration over space for that fixed time is just the d3x integration. And so we have now that this formula becomes explicit here. And then we have that for all solutions in the space of complex valued solutions of the Klein-Gordon equation, this resolution of the identity holds, and that becomes then explicitly, so basically plugging that expression for this kind of product into here, we obtain this equation. So the resolution of the identity spelled out explicitly, once we know what this is, becomes that equation. So the UN is this. And then that indefinite inner product here is this expression. Here we have UN star again, and then we have that inner product over here. Actually, I wrote them in the other sequence, right? So this is that term, and this is this term. And that is equal to f of x and t. Okay, so we know from the Dabou theorem that this is true. This equation will hold. We know from the Dabou theorem more precisely that there exists a set of functions un which will make that equation true. So now we interchange the summation and the integration over the space-like hypersurface. And so we interchange these two here. Then we have the integral d3x over here, summation in there. And at this point, we notice that on the left-hand side of this equation, the the f is evaluated at all x. I mean, we are integrating over all of the x's. Just a sec. I think this should be x prime here. We're integrating over all of the x prime. But this equation holds for just one time. I mean, we just pick one time here. So now, because remember, we have picked one space-like hypersurface in all of space-time. So we have picked one time, and then we integrate over all of space. Now, let us choose an arbitrary function g of x prime, completely arbitrary, but it's only dependent on space, not on time. Then there will exist a solution in the solution space to the Klein-Gordon equation, which has this function as its initial condition at the time t0, at the time at which we evaluate this equation here. And further, we can also require that this equation holds true. Remember that this g has nothing to do with that. That's just the metric here. And the reason why we can do that is that we are assuming that we have a globally hyperbolic space-time, where we have a well-defined Cauchy problem. If you know what, for a second-order differential equation, is the amplitude initially and also the derivatives, then that defines a solution in one-to-one correspondence. Every solution has these initial conditions, and the initial conditions gives you exactly one solution. So therefore, our equation star, this one, which is guaranteed to hold on the basis of Darboux theorem, gives us now, in terms of that completely arbitrary function g of x, gives us this equation here. I've just replaced the occurrences of that function f, which had to be a solution to the Klein-Gordon equation, by the occurrences of the g of x that fixes that solution. The reason I did that was that now the g of x is completely arbitrary. It's a completely arbitrary function of space. And since this equation here is supposed to be true for all functions g of x, it must be true that this is equal to the Dirac delta, right? Or technically, we can functionally differentiate that equation with respect to g, in which case we get a Dirac delta here and this stuff on the left. This is the equation that we have to prove. Okay, so the conclusion so far, we are almost done for today. I know it was pretty rough today. The conclusion so far was we can have the commutation relations obeyed, we can have hermiticity, and we can have the equations of motion. We can always solve them with this ansatz here, where the UK are solutions to the Klein-Gordon equation and the A have the standard commutation relations. If we can find solutions to the Klein-Gordon equation which sum up in this way to the Dirac delta, and as we just showed, there always exists such a U that will do it. There always exists such a set of functions un that will do it. Darboux's theorem, however, tells us that the Darboux bases are not unique. There were many choices, and that will have physical significance. So a quick outlook of the questions that we will address as the very next things. We showed that this crucial equation W, this one, can always be arranged to hold true at one point in time. Strictly speaking, that's what we showed. It might still be that the evolution is such that it's not true at a later time. What then? In fact, it's crucial for this equation to hold true at later time. It's crucial that the Klein-Gordon field is a free field, that it doesn't have a complicated potential like phi to the fourth, or that it doesn't couple to other fields. It wouldn't be true otherwise. It wouldn't be true that this is conserved. We will later show, the next lecture, that this condition remains true. If it's true at one point in time, it will be true at all later times for the free Klein-Gordon field, which is influenced only by gravity, but nothing else. But we need for that purpose to use the equation of motion, and we will see that it's only true if the equation of motion is that of a free field. Now, what does that mean? Does that mean that if the Klein-Gordon field is not free, then the commutation relations are not conserved in time? No, of course not. It just means that our ansatz will fail. Right? It just means that we can't succeed with our ansatz if the field has some non-trivial interactions with other fields or itself. Okay, but we will look into how that comes about and the relationship between the conservation of the commutation relations and unitarity. In fact, they are basically related by Noether's theorem. Right? A unitary invariance of a quantum theory is something like a symmetry. It's a U-infinity symmetry. And by Noether's theorem, there's got to be a conservation law. But what is conserved? Given that in a quantum theory, you can always do a unitary transformation, you get the same quantum theory. What is conserved is the commutation relations. Commutation relations are the conserved charges to the unitary symmetry of a quantum theory. And in this case, it matters here, right? Because what we are after is a conservation of commutation relations. And if the commutation relations were not conserved, it would mean that unitarity is violated. And we are not quite ready to take that step. So we conclude that the method is failing, that the ansatz is failing, not that the physics is failing. Okay, and then the big question, the next very big question is these basis functions that are guaranteed to exist by Darboux theorem and that will allow us to succeed with our ansatz are not unique. The math of it will be Bogoliubov transformations. Bogoliubov transformations get us from one set of solutions to the other set to any other set of solutions, and the physics of that is going to be the ambiguity in choosing or identifying what the vacuum state is. Okay, that's all for today. Questions? Yeah.
So here you basically solve Klein-Gordon equation on curved spacetime. So I was wondering, the spin of particles is connected to the Poincare group in flat spacetime. So what if you would do this for the Dirac equation? What would happen with the notion of spin of particles? Is it solved or?
Yes, you can put the Dirac equation on curved space-time. However, it's a quite non-trivial enterprise. And let's see, what would happen if we try to do it naively? Well, the Klein-Gordon, the Dirac equation, has gamma matrices. And their intercommutator is the metric on the right-hand side. But the metric in curved space-time could be all over the place. So it would seem that you have to find different gamma matrices for every different location in space-time. You'd have to have different gamma matrices. That would be really tedious.
If you use the Simon basis, as you did in the previous course.
Yes. So what you can then do is instead, you can you look at general relativity and you realize, I'm talking now to those who have not taken my course last term, right? Look at general relativity and then you ask, why is it that the metric tensor's components change when you change coordinate system? And the reason is that when you change coordinate system, you are motivated to change bases in your tangent space. Right? When originally the tangent space directions, the basis directions would be the dx0, dx1, dx2, dx3 directions, so the coordinate directions. If you now change to another coordinate system, then it would be natural to change the basis in your tangent space. But if you change the basis in the tangent space, it's natural to change the basis in the cotangent space. And it's natural to change the basis for all tensors accordingly. But it's only natural, it's not necessary. You can always choose whatever basis you want in your tangent and cotangent and tensor spaces, and you can keep your basis even when you change coordinates. That leads you to the framework of frames. And then in that framework, you can choose your metric to always take the same entries as the one in Cartesian coordinates in Minkowski space for an inertial observer. And then you can write down the Klein-Gordon equation in this framework, and that's possible, yeah. But But then you're committed to writing general relativity in a slightly different way, because then the degrees of freedom are not in the metric tensor, which always takes the form of eta mu, but now the degrees of freedom are in the change of basis matrix that maps you from the coordinate basis into the frame basis that diagonalizes the metric. So it's a different way of writing GR then. But in principle, yeah, you can do that. You can put fermions on curved space. Another way of looking at it is that you have to introduce a connection for parallel transporting spins in order to get the Dirac operator on curved space-time. Yeah. It's doable. Now, for our purposes, the main purpose of this course is to understand how, in the classical model, in the standard model of cosmology, the inhomogeneities in the universe are generated out of quantum fluctuations. And the picture is, at least up to now, who knows, is that it was mostly a scalar field, the inflaton field was responsible for that, and the scalar part of the metric. And then the tensor part of the metric is supposed to, but not confirmed yet, to have led to some polarization fluctuations. But so far we have not found a role for spin 1/2 in cosmology, that it would really have a big impact. I haven't seen that. It's basically because during inflation, a spin 1/2 particle wouldn't have its fluctuations amplified the way that a scalar field does, as we will see later on.
I'm a bit confused about one comment you made after the Darboux.
Mm-hmm.
You say we pick one of such bases. The theorem says like there exists at least one basis.
Mm-hmm.
So do we have another tool to say there will be more to satisfy that?
Yes, I will show you. Yes, yeah, because we can actually construct them with Bogoliubov transformations. We can easily construct them.
I'm going to use those transformations to construct another basis.
Yes. Yes, that's right. It will be constructive.
In slide 22, you exchanged the integral and the sum.
You're asking how dangerous that is?
Yeah. Especially because we don't know much about these functions.
Right. It's one of the more harmless ones. I can't exclude that it would be bad. But let's look at what it usually takes if you want to do that. You need something like dominated convergence. You need that the functions are sufficiently well behaved. And while it's true that you can write down sequences of functions that look pretty well behaved individually, but the sequence is badly behaved, you wouldn't really expect that here, because all those functions that we have here are basically glorified plane waves. They're all pretty much, curved space analogs of plane waves, and they are well behaved. So in particular, they are not going to grow out of bounds. But of course, in quantum field theory, the non-interchangeability of two limits is really a very important thing in some circumstances. In particular, when you derive the Feynman rules, as I will show in one of the last lectures, when you derive the Feynman rules for an interacting quantum field theory, then you do interchange two limits, of which we know we're not allowed to do that. It's just not right to do it. And the price we have to pay for that is that we then arrive at the Feynman rules are right, and they just represent a perturbative expansion. Now, if the two limits were interchangeable, then that perturbative expansion would converge. But since they don't really, you can't really exchange them, the perturbative expansion given by the Feynman rules is generally not convergent. It's only asymptotic. It's an asymptotic series, which means not everything is lost. For the first 20 or so orders in the perturbation theory, you are actually getting closer and closer to the true value. But then it starts diverging away from it and goes to infinity. So the reason why we get away with doing this, the reason why we get away with using Feynman rules at all is that perturbation theory is so hard. We can only do like up to 5th order or so. And then we have so many loops and bubbles and cycles in the Feynman graphs that we can no longer handle it. But if, for example, you look at quantum electrodynamics, where the coupling constant is like less than 1%, right, fine structure constant, you can work out how far the perturbation theory can be trusted, how high order you can go in perturbation theory, and you still approach the true value, and after that it will diverge. And I worked it out. For electrodynamics, it's about 20 orders of perturbation theory. And there's no way we are going to do 20 orders of perturbation theory, so the problem is not going to come up. You can just improve, improve, improve. But ultimately, if we could go to 100 orders of perturbation theory, we wouldn't. We would stop at 20. Because after that, the results would get worse and worse. But I'm anticipating stuff that we'll do much later in the course.